Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. The glowing clouds, where stars are born. Scattered throughout the galaxy are vast clouds of gas and dust, some spanning hundreds of light years across, glowing with ethereal colours against the darkness of space. These nebulae are the cosmic nurseries, where stars come into being, regions where the raw materials of the universe, hydrogen and helium from the Big Bang, mixed with heavier elements forged in previous generations of stars, gather, collapse, and ignite into new points of light. Understanding these stellar nurseries means understanding one of the most fundamental processes in the cosmos, the transformation of diffuse gas into concentrated spheres of nuclear fusion that will shine for millions or billions of years. The process begins with the molecular cloud, a region of space where gas has accumulated and cooled to temperatures only a few degrees above absolute zero. These clouds are dark when viewed in visible light because the dust mixed with the gas blocks starlight from behind, creating dark patches against the background glow of the Milky Way. But observe them in infrared or radio wavelengths, and they reveal intricate structures, filaments, cores, and clumps where the density varies, creating a complex web of material threaded throughout these regions. Molecular clouds are mostly hydrogen, but at the low temperatures found within them, individual hydrogen atoms have paired up to form molecular hydrogen, H2. This molecular form is more stable at cold temperatures, and these clouds also contain molecules that might seem surprising in the depths of space: carbon monoxide, water, ammonia, formaldehyde, and even more complex organic molecules. The chemistry occurring in these cold clouds is rich and varied, with molecules forming on the surfaces of dust grains and in the gas phase, building up a diverse molecular inventory over millions of years. Something must disturb these clouds to initiate star formation. A cloud can exist in a stable state for a long time, with internal pressure from the gas supporting it against its own gravity. But if the cloud is compressed, if its density increases beyond a critical threshold, gravity begins to win. This compression can come from several sources: a shockwave from a nearby supernova explosion, pushing through space, the compression created when spiral arms of the galaxy pass through the region, or even the radiation and winds from existing massive stars that can trigger collapse in adjacent cloud material. Once collapse begins, the cloud fragments into smaller pieces. A single large molecular cloud doesn't collapse into one giant star. Instead, it breaks apart into hundreds or thousands of individual, collapsing cores, each one potentially forming a star or a small system of stars. This fragmentation occurs because, as the cloud collapses, it develops instabilities. Regions that are slightly denser collapse a bit faster, pulling in material from their surroundings, and these growing density enhancements become the seeds of individual stars. Picture one of these collapsing cores. Initially, it might be 1/10 of a light year across, containing perhaps a few times the mass of our Sun, with a density barely above that of the surrounding cloud. As it contracts under its own gravity, the material falls inward, but it doesn't fall uniformly. The core rotates slowly, inherited from the overall rotation of the cloud, and as it contracts, conservation of angular momentum causes it to spin faster, just as a figure skater spins faster when pulling their arms inward. This rotation prevents all the material from falling directly onto the forming star at the center. Instead, material settles into a rotating disk around the protostar, a flattened structure where gas and dust orbit the central condensation. This is a protoplanetary disk, the structure from which planets will eventually form. The material in this disk gradually spirals inward, losing angular momentum through viscosity and magnetic effects, feeding the growing protostar at the center, while the outer portions of the disk may remain in orbit for millions of years. As the protostar grows, accumulating more and more mass from the infalling material, its center heats up. Gravitational potential energy converts to thermal energy as material falls inward, and the temperature and pressure at the core climb steadily. The protostar begins to glow, first emitting infrared radiation, then gradually becoming brighter as it contracts. At this stage, it's not yet a true star. No nuclear fusion occurs at its core, but it's radiating energy produced by gravitational contraction, a process called Kelvin-Helmholtz contraction. The infalling material doesn't simply accumulate smoothly. Young protostars are violent, turbulent objects. They generate powerful magnetic fields that interact with the surrounding disk and the infalling gas. These magnetic fields can launch jets, narrow streams of gas that shoot outward from the poles of the protostar at speeds of hundreds of miles per second. These jets plow into the surrounding molecular cloud, creating bow shocks where they collide with the ambient gas, heating it and causing it to glow. These glowing regions, called Herbig-Haro objects, appear as bright knots and filaments near young stars, moving visibly over periods of years as the jets evolve and push through the surrounding gas. The jets serve an important function. They carry away angular momentum and energy, allowing material in the disk to continue falling onto the protostar. Without this mechanism to remove angular momentum, the disk would simply spin faster and faster, and accretion would halt. The protostar continues to accrete material and contract for hundreds of thousands to millions of years, depending on its mass. During this time, it's deeply embedded in the cloud that spawned it, hidden from view at visible wavelengths by the cocoon of gas and dust surrounding it. Infrared observations can penetrate this obscuration, revealing the glowing protostar and its disk within the dark cloud. These embedded protostars mark the earliest visible stages of star formation, objects that are still gaining mass and have not yet ignited nuclear fusion. Eventually, the temperature and pressure at the protostar's core reach a critical threshold, typically around 10 million degrees. At this point, protons begin to fuse, creating helium and releasing energy through nuclear fusion. The protostar becomes a true star, entering what's called the main sequence, where it will spend the majority of its life fusing hydrogen into helium. The energy released by fusion creates an outward pressure that finally halts the gravitational contraction, and the star settles into a stable configuration where gravity and pressure are balanced. When the star ignites, it begins to affect its surroundings dramatically. The radiation from the young star heats the surrounding gas and dust. Ultraviolet light from the star ionizes hydrogen atoms, stripping electrons away and creating a region of ionized gas called an H2 region. These ionized regions glow with a characteristic reddish-pink color, the result of electrons recombining with protons and cascading down through energy levels, emitting light at specific wavelengths. This is the glow we see in many famous nebulae: the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, vast regions of ionized gas illuminated by the intense radiation from young hot stars. If the star is particularly massive and hot, more than about 8 times the Sun's mass, it produces copious ultraviolet radiation that can ionize gas over large volumes of space. A single massive star can create an H2 region spanning dozens of light years. Multiple massive stars forming in the same region create even larger ionized bubbles. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, glows because of a handful of massive young stars at its center, whose radiation ionizes the surrounding molecular cloud. The radiation pressure and stellar winds from young stars don't just make the cloud glow, they also begin to push the gas away, clearing out cavities in the molecular cloud. This feedback can actually trigger more star formation in the surrounding material. As the expanding HII region compresses gas at its edges, it can push that material above the density threshold needed for collapse, triggering new rounds of star formation in a process that propagates through the cloud. Young star clusters often show evidence of sequential star formation, with the oldest stars at the center surrounded by progressively younger stars farther out. The initial generation of stars alters the cloud, compressing and heating gas at the periphery, triggering the formation of the next generation. This process continues until the cloud is either dispersed entirely by the radiation and winds from the young stars, or exhausted of material dense enough to form new stars. The most massive stars, those dozens of times more massive than the Sun, live brief but spectacular lives. They burn through their nuclear fuel in just a few million years, and then explode as supernova, catastrophic events that briefly outshine entire galaxies. These explosions inject tremendous energy into the surrounding gas, heating it to millions of degrees, accelerating it to thousands of miles per second, and enriching it with heavy elements created in the star and in the supernova explosion itself. Carbon, oxygen, silicon, iron, and even heavier elements like gold and uranium. These heavy elements mix into the molecular cloud, changing its composition. The next generation of stars that forms from this enriched material will contain more heavy elements than the previous generation. This process of stellar birth, life, death, and rebirth has been occurring for over 13 billion years, gradually enriching the interstellar medium with heavy elements. The earliest stars in the universe formed from nearly pure hydrogen and helium. Stars forming today, including our Sun, contain about 2% heavy elements by mass, a small fraction, but crucial for the formation of planets, and ultimately for the existence of life. The dust mixed throughout these star-forming clouds plays a crucial role beyond just blocking light. The tiny grains, typically less than a micrometer in size, serve as surfaces where molecules can form. Hydrogen atoms landing on a grain's surface can find each other and bond, forming molecular hydrogen far more efficiently than they could in the gas phase. Water molecules, carbon monoxide, and more complex organics also form on grain surfaces, then evaporate back into the gas or become incorporated into forming stars and planets. Star formation is not perfectly efficient. Only a small fraction of the gas in a molecular cloud, perhaps 1 to 10%, actually ends up in stars. The rest is either dispersed by stellar feedback, ejected by stellar winds and supernova explosions, or simply never reaches densities high enough to collapse. The molecular clouds we observe are continuously evolving, with some regions collapsing to form stars while other regions are being cleared out by the very stars that recently formed within them. Different regions of the galaxy have different rates of star formation. The spiral arms, where gas is compressed as it enters these density waves, show enhanced star formation, lighting up with the blue glow of young hot stars and the red emission from H2I regions. The galactic center, with its extreme environment and powerful tidal forces, has intense star formation, but also extreme feedback that can suppress star formation. The outer regions of the galaxy, with less gas available, form stars more slowly. Star formation is occurring right now throughout the Milky Way and throughout the universe. In distant galaxies, billions of light years away, we observe intense starbursts where entire regions of galaxies are forming stars at rates thousands of times higher than in our galaxy, triggered by galaxy collisions or mergers that compress enormous quantities of gas. The stars forming in those distant galaxies emit light that has travelled across most of the universe's history to reach our telescopes, showing us star formation as it occurred when the universe was much younger. The glowing nebulae we see in telescopes and photographs are not static monuments, but dynamic regions of ongoing transformation. The clouds are collapsing, the protostars are growing, the newly formed stars are dispersing the clouds that gave them birth. Within a few million years, the blink of an eye on cosmic timescales, a star-forming region transforms from a dark molecular cloud to a bright cluster of young stars, to a dispersed association of stars gradually spreading through the galaxy, each one carrying forward the legacy of its birth, enriching future generations of clouds with the elements created during its life, continuing the cycle of stellar birth and death that has shaped the galaxy since its formation billions of years ago. The cosmic web that connects galaxies. When you look up at the night sky, the stars appear scattered across the darkness in what seems like a random pattern. Galaxies, those island universes containing billions of stars, seem to float in isolation, separated by vast gulfs of empty space. But zoom out far enough, pull back your perspective to encompass not just our galaxy or our local group of galaxies, but thousands, then millions, then billions of galaxies, and an extraordinary pattern emerges. The universe is not random at all. It's organized into a structure so vast and intricate that it resembles a three-dimensional spider's web stretching across the entire observable cosmos. This structure, called the cosmic web, represents the largest known organizational pattern in the universe. Picture it in your mind: long filaments of galaxies stretching across hundreds of millions of light years, connecting at massive nodes where galaxy clusters gather. Between these filaments lie enormous voids, regions of space so empty that they contain almost no galaxies at all. The filaments themselves are like highways of matter, channels along which gas flows and galaxies form, creating luminous threads that trace out the underlying architecture of space itself. The story of the cosmic web begins in the earliest moments after the Big Bang. In those first fractions of a second, the universe was nearly uniform, filled with hot plasma that was almost, but not quite, perfectly smooth. Tiny quantum fluctuations, variations in density that were only 1 part in 100,000, existed throughout this primordial material. These minuscule differences seemed insignificant, but they contained the seeds of everything that would come after. As the universe expanded and cooled, gravity began to amplify these tiny variations. Regions that were even slightly denser than average had slightly stronger gravity, which pulled in surrounding matter, making them denser still. This process fed on itself, with denser regions becoming denser over time, while less dense regions became emptier as their matter drained away toward the dense areas. But matter didn't just collapse into points, it collapsed along preferred directions, following the geometry dictated by the initial distribution of fluctuations. Imagine pouring cream into coffee and watching it swirl and fold into complex patterns before mixing completely. The early universe underwent something similar, but instead of mixing, the patterns froze into place, held there by gravity. Matter flowed along the paths of least resistance, streaming toward concentrations of mass, creating sheets and filaments rather than distributing itself uniformly. Dark matter played a crucial role in creating this web. This mysterious substance, which doesn't emit or absorb light but exerts gravitational force, makes up about 85% of all matter in the universe. Dark matter began clustering earlier than normal matter because it doesn't interact with light or other radiation. It formed a gravitational scaffolding, a framework of invisible mass and normal matter. The hydrogen and helium gas that would eventually form stars and galaxies fell into the gravitational wells created by this dark matter framework. The filaments of the cosmic web are not thin lines, but rather thick structures, typically about 20 to 30 million light years across, and stretching for hundreds of millions of light years in length. Along these filaments, galaxies form like beads on a string, though the string itself is made of dark matter with tendrils of gas threading through it. The gas in these filaments exists in a warm to hot state, typically between 100,000 and 10 million degrees, hot enough that it emits X-rays, but not dense enough to be easily observable. At the intersections where multiple filaments meet, enormous galaxy clusters form. These are the cities of the cosmic web, containing hundreds or even thousands of galaxies bound together by gravity. The largest galaxy clusters can contain as much mass as 1,000,000 billion suns, most of it in the form of dark matter, with substantial amounts of hot gas filling the space between galaxies. These clusters mark the nodes of the web, the places where matter has concentrated most densely. Between the filaments lie the cosmic voids, vast regions of space that are remarkably empty. A typical void might be 150 million light-years across and contain very few galaxies. These aren't completely empty. They still contain dark matter and some diffuse gas, but their density is only about 10 to 20% of the average density of the universe. Voids expand over time as matter continues to flow out of them toward the filaments and clusters, making them emptier with each passing billion years. The cosmic web reveals itself to astronomers through large-scale galaxy surveys. Telescopes map the positions of millions of galaxies, measuring not just where they appear in the sky, but also how far away they are. This three-dimensional mapping shows the web's structure clearly. Some of the most famous structures include the Sloan Great Wall, a concentration of galaxies stretching across 1.4 billion light-years, and the Hercules Corona Borealis Great Wall, which spans an almost incomprehensible 10 billion light-years. Our own Milky Way galaxy sits within this web, part of what's called the Local Group, a small collection of about 50 galaxies, including the Andromeda Galaxy and various smaller dwarf galaxies. This local group is located on the outskirts of the Virgo supercluster, a massive structure containing thousands of galaxies. Recent mapping has revealed that the Virgo supercluster is itself part of an even larger structure called Laniakea, a supercluster of superclusters spanning 520 million light-years and containing the mass of about 100,000 trillion suns. The gas flowing through the cosmic web carries matter from the voids into the filaments, and from the filaments into the galaxy clusters. This flow is not gentle. Gas moving through the filaments can reach speeds of several hundred kilometers per second, and when streams of gas collide at cluster locations, shock waves heat the gas to tremendous temperatures. These shock waves, called accretion shocks, occur at the boundaries of clusters where the web feeds new material into these gravitationally bound systems. Galaxies forming within the filaments have different characteristics than galaxies forming in the voids or clusters. Filament galaxies have better access to the gas supply flowing through the web, which allows them to continue forming stars for longer periods. Cluster galaxies, surrounded by hot gas and interacting frequently with other galaxies, often exhaust their star-forming fuel more quickly. Void galaxies, isolated and with limited gas supply, tend to be smaller and less luminous. The web is not static. It evolves over cosmic time as gravity continues to pull matter along its channels. Computer simulations of the universe's evolution show that the web was less pronounced in the early universe and has become more defined over billions of years. The voids have expanded. The filaments have thinned in some places while becoming more pronounced in others, and the galaxy clusters have grown larger as they consume matter from the surrounding web. Dark energy complicates this picture. This mysterious force which causes the universe's expansion to accelerate works against gravity's tendency to pull matter together. While gravity tries to make the web more concentrated, dark energy pushes space apart. The current era represents a transition. For the first several billion years after the Big Bang, gravity dominated and the web continued to grow more structured. But as dark energy's influence has grown stronger over time, it has begun to limit further structure growth. In the far future, dark energy will win, pulling the filaments apart and eventually isolating each galaxy cluster as an island in an ever-expanding sea of space. Scientists study the cosmic web using multiple techniques. Optical telescopes map the positions of galaxies. Radio telescopes detect the neutral hydrogen gas in and around galaxies. X-ray telescopes observe the hot gas in galaxy clusters and filaments. By combining these different views, astronomers build up a comprehensive picture of where matter exists and how it moves through the web's structure. The web also serves as a cosmic laboratory for studying dark matter. The way galaxies move within filaments and clusters, and the bending of light from distant objects as it passes through the web's mass concentrations, both provide information about the distribution of dark matter. These observations have helped confirm that dark matter exists, and have constrained theories about what dark matter might be, even though its fundamental nature remains one of physics' deepest mysteries. On the very largest scales, the cosmic web shows a surprising degree of uniformity. While the web has complex structure on scales up to a few 100 million light-years, if you average over regions a billion light-years or larger, the universe looks remarkably similar in all directions. This homogeneity on the largest scales supports the cosmological principle, the idea that on sufficiently large scales, the universe is essentially the same everywhere, with no preferred locations or directions. The web continues to influence galaxy evolution today. Our own galaxy, the Milky Way, is being pulled through space by the gravitational attraction of the web's structure. We're falling toward the Virgo cluster at about 400 kilometers per second, and at the same time, our entire local supercluster is being pulled toward an even more massive concentration of galaxies in the direction of the constellations Centaurus and Hydra, a region astronomers call the Great Attractor. Understanding the cosmic web means understanding how the universe transformed from a nearly smooth state shortly after the Big Bang into the rich, structured cosmos we see today. The web is a fossil record of the universe's history, preserving information about the initial conditions that existed billions of years ago, and documenting the ongoing battle between gravity, trying to pull matter together, and cosmic expansion, trying to spread it apart. Every galaxy in the night sky exists where it does because of this vast structure, this intricate architecture that connects everything in the universe into one enormous, evolving pattern. The afterglow of the Big Bang. Throughout the entire universe, in every direction you could possibly look, there exists a faint glow of microwave radiation that fills all of space. This radiation isn't coming from stars or galaxies or any object in particular. It's coming from everywhere at once, a ghostly remnant from the earliest moments of cosmic history. This is the cosmic microwave background, the oldest light in the universe, and it carries within it a snapshot of what the cosmos looked like when it was just 380,000 years old, a mere infant compared to its current age of 13.8 billion years. To understand this afterglow, picture the universe in its earliest moments. At the very beginning, everything that exists now, all the matter and energy in hundreds of billions of galaxies, was compressed into an infinitesimally small point. The Big Bang wasn't an explosion in space, but rather an expansion of space itself. In those first fractions of a second, the universe was unimaginably hot and dense, so hot that matter as we know it couldn't exist. There were no atoms, no nuclei, not even stable protons or neutrons. There was only a seething soup of fundamental particles and energy, all in thermal equilibrium at temperatures of trillions upon trillions of degrees. As the universe expanded, it cooled, following a fundamental principle of thermodynamics. Think of how a spray can get cold when you release the compressed gas inside. Expansion causes cooling. The universe cooled rapidly in those early moments, dropping from inconceivable temperatures down to merely billions of degrees within the first few minutes. At this point, conditions became cool enough for protons and neutrons to stick together, forming the nuclei of the lightest elements, primarily hydrogen, some helium, and trace amounts of lithium and beryllium. This period, called Big Bang nucleosynthesis, lasted only about 17 minutes, but it determined the basic chemical composition of the universe for hundreds of millions of years to come. But even after nuclei formed, the universe was still far too hot for atoms to exist. Free electrons zipped through space at tremendous velocities, and any time they got near a nucleus, the ambient heat would knock them away before they could settle into orbit. The universe was filled with a plasma, a mixture of atomic nuclei and free electrons, and this plasma was opaque to light. Photons couldn't travel far before colliding with a free electron and scattering in a new direction. Light was trapped, bouncing endlessly between particles in a cosmic fog that filled all of space. For the next 380,000 years, the universe continued expanding and cooling, but it remained opaque. The temperature dropped gradually from millions of degrees down to thousands of degrees. Then at around 3,000 degrees Kelvin, still hot enough to melt any metal, something remarkable happened. The universe had finally cooled enough for electrons to combine with nuclei and form stable atoms. This moment is called recombination, though that's actually a misnomer since the electrons and nuclei were combining for the first time, not recombining. When recombination occurred, the nature of the universe changed fundamentally. With electrons now bound into atoms, there were suddenly far fewer free charged particles for photons to scatter off of. The cosmic fog cleared almost instantaneously on cosmic timescales. Light that had been trapped, scattering endlessly through the plasma, was suddenly free to travel unimpeded through space. The universe became transparent. The photons that were released at that moment of recombination have been travelling through space ever since. They filled the entire universe then, and they fill the entire universe now. These photons form the cosmic microwave background. They are the afterglow of the Big Bang, the first light that could freely travel through the cosmos. But here's the crucial part. Those photons have been stretched by the expansion of the universe. When they were released 13.8 billion years ago, they were primarily visible light and infrared radiation, corresponding to the 3,000 degree temperature of the universe at recombination. But as space itself expanded, the wavelengths of these photons were stretched along with it. Light that was once visible orange has been stretched into infrared, then into far infrared, and finally into microwave radiation. The cosmic microwave background today corresponds to a temperature of just 2.7 degrees above absolute zero, 2.7 Kelvin. This stretching of light by the expansion of space is called cosmological redshift, and it's one of the most direct pieces of evidence for the Big Bang theory. The universe has expanded by a factor of about 1,100 since recombination, and the wavelength of the cosmic microwave background radiation has been stretched by exactly this same factor. What was once a hot glow of visible light has become a cold bath of microwave radiation. The cosmic microwave background is incredibly uniform. No matter which direction you look in the sky, the temperature is almost exactly the same, 2.725 Kelvin, with variations of only about 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous. There were no large structures, no concentrations of matter, just an almost perfectly uniform distribution of hydrogen and helium gas filling all of space. But those tiny variations, those fluctuations of 1 part in 100,000, are extraordinarily important. They represent slight differences in density and temperature in the primordial plasma. Some regions were slightly denser and hotter, others slightly less dense and cooler. These fluctuations were the seeds of all structure in the universe today. The denser regions had slightly stronger gravity, which allowed them to attract more matter over time. Over hundreds of millions of years, these tiny density differences grew, eventually collapsing to form the first stars, then galaxies, then galaxy clusters, and ultimately the entire cosmic web of structure we see today. When astronomers map the cosmic microwave background in detail, they're seeing a snapshot of these primordial fluctuations. Sophisticated satellites, equipped with incredibly sensitive detectors, measure the temperature of the cosmic microwave background across the entire sky, creating maps that show warmer and cooler spots. These maps look like mottled patterns of slightly different colours, almost like abstract art, but they're actually baby pictures of the universe, showing the distribution of matter when the cosmos was just 380,000 years old. The patterns in the cosmic microwave background aren't random. They have specific statistical properties that depend on the fundamental parameters of the universe. How much normal matter exists, how much dark matter, how much dark energy, the rate of expansion, the curvature of space, and more. By analysing these patterns in exquisite detail, cosmologists can measure these parameters with remarkable precision. The cosmic microwave background has become the single most important tool for determining the basic properties of our universe. One of the most striking features visible in cosmic microwave background maps is the presence of acoustic oscillations, essentially sound waves in the primordial plasma. Before recombination, the plasma was hot and under tremendous pressure from radiation. Regions that were slightly denser had stronger gravity pulling inward, but they also had stronger radiation pressure pushing outward. These competing forces created oscillations, with dense regions compressing and then rebounding, creating waves that propagated through the plasma, much like sound waves travel through air. These acoustic oscillations were frozen into the distribution of matter at the moment of recombination. The characteristic scale of these oscillations, the typical distance between peaks and troughs, shows up as a specific pattern in the cosmic microwave background, radiation background, temperature fluctuations. By measuring this pattern precisely, astronomers can determine how far these sound waves had travelled by the time of recombination, which in turn tells them about the geometry and expansion rate of the universe. The cosmic microwave background also has a subtle property called polarization. Light can be polarized, its electric field can oscillate in a preferred direction, and the cosmic microwave background photons carry polarization information from the moment they were released. This polarization was created when the photons scattered off electrons for the last time before recombination. The pattern of polarization across the sky carries additional information about conditions in the early universe, including potentially evidence of gravitational waves from the inflationary period that may have occurred in the first tiny fraction of a second after the Big Bang. There are actually two types of polarization patterns in the cosmic microwave background, called E modes and B modes. E modes are relatively easy to detect and have been thoroughly mapped. B modes are much fainter and harder to detect, but they're particularly interesting because primordial gravitational waves would create a specific B mode pattern. Detecting this signal would provide direct evidence for cosmic inflation and would open a window into physics at energy scales far beyond what we can achieve in particle accelerators on Earth. The cosmic microwave background isn't perfectly smooth in its distribution across the sky. There's a slight asymmetry, a dipole pattern, where one side of the sky is slightly hotter and the other slightly cooler. This dipole is caused by the motion of our solar system through space. We're moving at about 370 kilometers per second relative to the cosmic microwave background, carried along by the motion of the Sun around the galaxy, the motion of the galaxy through the local group, and the motion of the local group through the universe. This motion causes the cosmic microwave background to appear slightly blue-shifted, and therefore hotter in the direction we're moving toward, and slightly red-shifted, and cooler in the direction we're moving away from. Once this dipole is removed from the data, along with contamination from our own galaxy's emission, What remains are the primordial fluctuations, the image of the universe as it was 380,000 years after the Big Bang. These fluctuations exist on multiple scales, from features spanning large portions of the sky down to the smallest angular scales that satellites can resolve. Each scale carries different information about the early universe and the physical processes that shaped it. The cosmic microwave background has also been used to test fundamental physics. The spectrum of the radiation, how much energy exists at each wavelength, matches a perfect blackbody spectrum, more precisely than any artificial source humans have ever created. This perfect blackbody spectrum is exactly what's expected from matter and radiation in perfect thermal equilibrium, providing strong confirmation that the early universe was indeed in this state. Photons from the cosmic microwave background pass through everything. Right now, billions of these ancient photons are streaming through your body every second, traveling through space for nearly 14 billion years before encountering the atoms in your cells. They pass through largely without interaction because microwave radiation interacts very weakly with ordinary matter at everyday temperatures. The entire Earth is bathed in this ancient light, as is every planet, every star, every galaxy. It's a universal background that permeates all of existence. The discovery of the cosmic microwave background in 1964 was accidental. Two radio astronomers, Arno Penzias and Robert Wilson, were testing a sensitive radio antenna and kept detecting a persistent noise that came from all directions and wouldn't go away no matter what they did. They initially thought it might be interference from nearby New York City, or perhaps noise from the electronics, or even from bird droppings on the antenna. Only when they consulted with theoretical physicists did they realize they had detected the afterglow of the Big Bang, earning them the Nobel Prize. This radiation has been cooling for billions of years and will continue cooling forever. As the universe expands, the cosmic microwave background will be stretched to longer and longer wavelengths, eventually becoming radio waves, then longer wavelengths still. Its temperature will approach closer and closer to absolute zero, but will never quite reach it, always remaining as a faint reminder of the hot, dense state from which our universe emerged, carrying information about cosmic dawn across the vastness of space and time. How stars create light and heat. Every star you see in the night sky is a massive nuclear furnace, a sphere of gas so hot and dense at its core that atoms are torn apart and fused back together in reactions that release staggering amounts of energy. The light that reaches your eyes from even the nearest star beyond our sun has travelled for years through the void of space, carrying energy that was created in the unimaginable heat and pressure at that star's core. Understanding how stars create this light and heat means understanding one of the most fundamental processes in the universe, one that has been lighting the cosmos for billions of years and will continue for billions more. Begin at the heart of a star, the core, where conditions are almost beyond comprehension. In our sun, the temperature at the centre reaches about 27 million degrees Fahrenheit. The pressure is equally extreme, about 250 billion times the atmospheric pressure at Earth's surface. Under these conditions, matter behaves in ways completely unlike anything we experience in daily life. The gas is so hot that atoms cannot exist as atoms. Electrons are stripped away from their nuclei, creating a plasma where negatively charged electrons and positively charged nuclei move independently through a churning, seething mass. At these temperatures and pressures, atomic nuclei that would normally repel each other, they're all positively charged, and like charges repel, move so fast that they occasionally collide with enough energy to overcome this electrical repulsion. When hydrogen nuclei, which are simply protons, collide at these tremendous speeds, they can fuse together. This is nuclear fusion, and it's the source of all the energy a star produces. The most common fusion process in stars like our Sun is called the proton-proton chain, Picture two protons colliding at enormous speed in the star's core. Usually, they just bounce off each other, repelled by their mutual positive charge. But occasionally, very rarely, quantum mechanics allows something remarkable to happen. The two protons fuse, and in that instant, one of them transforms into a neutron through a process involving the weak nuclear force. This creates a nucleus of heavy hydrogen, called deuterium, consisting of one proton and one neutron bound together. This single fusion event releases energy in multiple forms. A positron is ejected, the antimatter counterpart of an electron. A neutrino, an almost massless particle that barely interacts with anything, streams away at the speed of light, and energy is released as gamma-ray radiation, the most energetic form of light. The positron almost immediately encounters a regular electron, and they annihilate each other in a burst of energy. The neutrino escapes the star entirely, passing through all the overlying layers as if they weren't there, reaching space in just a few seconds. But this is only the first step. The deuterium nucleus that formed doesn't last long on its own. It quickly collides with another proton and fuses with it, creating a nucleus of helium-3, which has two protons and one neutron. This fusion releases more energy, this time in the form of a gamma ray. Finally, two helium-3 nuclei collide and fuse, forming ordinary helium-4, which has two protons and two neutrons, and releasing two protons back into the mix to start the process over again. The net result of all these steps is that 4 hydrogen nuclei have been converted into one helium nucleus. And here's the crucial part. The helium nucleus weighs slightly less than the 4 hydrogen nuclei that went into making it. About 0.7% of the mass has disappeared. Where did it go? It was converted into energy, according to Einstein's famous equation, E equals mc squared. That tiny fraction of mass, when multiplied by the speed of light squared, represents an enormous amount of energy. In our Sun, this process converts about 600 million tons of hydrogen into helium every single second. About 4 million tons of matter are completely converted into energy each second. This has been happening for about 4.6 billion years, and the Sun has enough hydrogen fuel to continue for another 5 billion years or so before it exhausts the hydrogen in its core. The energy released in these fusion reactions, created at the core of the star, must somehow make its way to the surface, to be radiated into space as light and heat. This journey is neither quick nor straightforward. The gamma rays produced in the core don't simply stream to the surface. The star's interior is incredibly dense, and a gamma ray photon can't travel far before it collides with an electron or an atomic nucleus. When a high-energy gamma-ray photon hits an electron, it typically gets absorbed and then re-emitted, but not necessarily in the same direction, and often at a slightly lower energy. The photon bounces around randomly, absorbed and re-emitted countless times, following what scientists call a random walk. Each interaction changes the photon's direction randomly, so it might move inward toward the core just as often as it moves outward toward the surface. This random walk means that energy takes an extraordinarily long time to travel from the core to the surface. A photon of light can travel from the Sun to Earth, a distance of 93 million miles, in about 8 minutes. But that same photon trying to escape from the Sun's core to its surface, a distance of only about 400,000 miles, takes somewhere between 100,000 and a million years. The exact number is uncertain because the path is so random and complex, involving countless billions of interactions. As the energy works its way outward through this radiative zone, the photons gradually lose energy with each interaction. The high-energy gamma rays from the core become X-rays, then ultraviolet light, then visible light, and eventually include infrared radiation. By the time the energy reaches the outer portions of the star, it has been divided and redistributed among countless photons of various energies. About 2/3 of the way out from the Sun's core, the nature of energy transport changes. The temperature has dropped to the point where atoms can hold onto some of their electrons, and the gas becomes more opaque. In this outer region, called the convection zone, energy is transported primarily by the physical motion of hot gas rather than by radiation. Hot plasma rises toward the surface, cools, and then sinks back down, creating vast circulation cells. Think of a pot of boiling water with bubbles of hot water rising and cooler water sinking, but on a stellar scale where individual convection cells can be larger than Earth. This convection brings hot material from the interior up to the photosphere, the visible surface of the star. Here, finally, energy can escape into space. The photosphere is still incredibly hot by earthly standards, about 10,000 degrees Fahrenheit on the Sun, but it's cool enough that photons can finally stream away into space without being immediately reabsorbed. The light that leaves the photosphere carries information about the star's surface temperature in its colour and spectrum. Hotter stars emit more blue and ultraviolet light, appearing blue or white to our eyes. Cooler stars emit more red and infrared light, appearing orange or red. Our Sun, with a surface temperature around 10,000 degrees, emits most of its energy in the visible part of the spectrum, peaking in the green-yellow range, though it appears white or slightly yellow to our eyes because it emits all colours of visible light. Not all stars use the same fusion process as our Sun. In more massive stars with hotter cores, a different set of reactions called the CNO cycle dominates. This cycle uses carbon, nitrogen, and oxygen nuclei as catalysts to fuse hydrogen into helium. The carbon, nitrogen, and oxygen aren't consumed in the process. They're regenerated at the end of the cycle, but their presence allows the fusion to proceed more rapidly at higher temperatures. Very massive stars can burn through their hydrogen fuel in just a few million years, compared to the Sun's 10 billion year lifetime. The energy output of a star is precisely balanced with its gravity. Gravity tries to compress the star, but the pressure from the hot gas, heated by fusion, pushes outward. These forces are in equilibrium, which is why stars are stable over long periods. If fusion produces too much energy, the star expands and cools slightly, slowing the fusion rate. If fusion slows down, the star contracts and heats up, increasing the fusion rate. This self-regulating mechanism keeps stars stable. The heat generated in a star's core doesn't just produce light, it creates the pressure that holds the star up against its own gravity. Without fusion, a star would collapse under its own weight. This is what happens when a star runs out of fuel. The fusion stops, the pressure drops, and gravity takes over, leading to dramatic events like supernova explosions or the formation of dense stellar remnants. Different layers of the star have vastly different temperatures. The core, where fusion occurs, is the hottest. The temperature decreases as you move outward through the radiative zone and convection zone. The photosphere, the visible surface, is the coolest part of the star proper, though above it lies the chromosphere and corona, regions of the star's atmosphere that are paradoxically hotter than the surface, heated by magnetic fields and shock waves rather than by radiation from below. The amount of energy a star produces is staggering. Our Sun outputs about 386 billion megawatts of power every second. That's more energy than humanity has used in its entire history, released every single second. And the Sun is actually a fairly average, middle-sized star. Some massive stars output 1,000,000 times more energy than the Sun, burning so bright and hot that they exhaust their fuel and die in just a few million years. Every photon of sunlight that warms your face, every ray that allows plants to photosynthesize and create the oxygen you breathe, every bit of light that illuminates the day, began as a fusion reaction in the Sun's core. The energy in that light was created when hydrogen nuclei overcame their electrical repulsion and fused into helium, converting a tiny amount of mass into energy. That energy then spent hundreds of thousands of years bouncing randomly through the Sun's interior before finally reaching the surface and streaming across space to Earth. This process of creating light and heat through nuclear fusion is happening right now in hundreds of billions of stars in our galaxy alone, and in countless more stars throughout the universe. It's been happening since the first stars formed a few 100 million years after the Big Bang, and it will continue for trillions of years into the future, until the last stars finally exhaust their fuel and fade away, leaving the universe dark and cold. But for now, and for the foreseeable future, the universe is filled with light and heat, gifts of the fusion fires burning in the hearts of stars. How life could exist on other planets. For billions of years, Earth has been teeming with life, from microscopic bacteria in the deepest ocean trenches to massive blue whales swimming through the seas, from fungi spreading through forest soil to humans building cities and reaching for the stars. But Earth is just one planet orbiting one star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. The question that haunts astronomers, biologists, and anyone who has ever looked up at the night sky is simple yet profound. Could life exist somewhere else? And if it does, what would it need to survive? The search for life beyond Earth begins with understanding what life actually requires. On Earth, all known life shares certain fundamental characteristics. Life requires liquid water as a solvent, a medium in which chemical reactions can occur. It needs a source of energy, whether from sunlight through photosynthesis or from chemical reactions in deep-sea hydrothermal vents. It requires raw materials, elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur that form the building blocks of proteins, DNA, and cell membranes. And it needs time, stable conditions lasting long enough for life to emerge from non-living chemistry and evolve into complex forms. Water stands out as the most critical requirement for life as we know it. Water is an exceptional solvent, capable of dissolving more substances than almost any other liquid. Its unique properties, remaining liquid across a wide temperature range, expanding when it freezes, having strong surface tension, make it ideal for biochemistry. Water molecules interact with each other and with other molecules in ways that facilitate the complex chemistry life requires. Every known organism on Earth, from the simplest bacterium to the most complex animal, depends on liquid water. This dependence on water defines what astronomers call the habitable zone around every star, the range of distances where a planet's surface temperature allows water to remain liquid. For our Sun, this zone extends roughly from just inside Earth's orbit to just beyond Mars. Venus orbits too close. Despite having had water in its distant past, the intense solar heating drove a runaway greenhouse effect that boiled away the oceans and left a hellish world with surface temperatures hot enough to melt lead. Mars orbits near the outer edge, cold enough that most water exists as ice, though liquid water might occasionally form in certain locations under special conditions. But the habitable zone looks different around different types of stars. Red dwarf stars, the most common stars in the galaxy, are much cooler and dimmer than our Sun. Their habitable zones lie much closer in. A planet might orbit only a few million miles from its star, yet still maintain temperatures suitable for liquid water. This close orbit creates challenges. The planet would likely become tidally locked, with one side permanently facing the star in eternal daylight, while the other freezes in perpetual darkness. Red dwarfs also tend to be more active, producing powerful flares that could strip away planetary atmospheres. Yet despite these challenges, red dwarfs are so numerous and long-lived, some will shine for trillions of years, that they represent countless opportunities for life to emerge. Larger, hotter stars have habitable zones farther out, but these stars burn through their fuel quickly, living only millions or billions of years rather than the tens of billions of years that red dwarfs enjoy. This might not provide enough time for complex life to evolve. On Earth, life emerged relatively quickly, within the first billion years, but complex multicellular life took nearly 3 billion years to appear. Intelligence and technology took even longer. A planet orbiting a massive, short-lived star might develop microbial life, but never progress beyond that before its star exhausts its fuel and dies. The atmosphere plays a crucial role in making a planet habitable. Earth's atmosphere provides pressure that keeps water liquid at the surface. Without atmospheric pressure, water would instantly boil away in the vacuum of space or freeze solid at low temperatures. The atmosphere also provides greenhouse warming. Without it, Earth's average temperature would be well below freezing despite being in the habitable zone. Too little greenhouse effect and a planet freezes. Too much and it becomes an inferno like Venus. The balance must be just right. Planetary mass matters significantly. A planet too small cannot hold onto an atmosphere. Its weak gravity allows atmospheric gases to escape into space. Mars demonstrates this problem. Mars once had a thicker atmosphere and liquid water flowing on its surface, carving the river valleys and lake beds that spacecraft have photographed. But Mars is only about 11% of Earth's mass, and over billions of years, its atmosphere gradually escaped. The loss accelerated because Mars lacks a strong magnetic field to shield the atmosphere from the solar wind, the stream of charged particles from the Sun that can strip away atmospheric gases from unprotected planets. A planet too large faces different problems. If a planet grows massive enough, it begins capturing hydrogen and helium directly from the protoplanetary disk during formation, becoming a gas giant like Jupiter rather than a rocky world with a solid surface. Some theories suggest that planets slightly more massive than Earth, called super-Earths, might actually be better for life than Earth itself. Their stronger gravity could hold thicker atmospheres, providing more greenhouse warming and allowing habitable zones to extend farther from their stars. Their larger size might also mean more volcanic activity, recycling nutrients and maintaining atmospheric composition over longer timescales. Plate tectonics, the process by which Earth's crust is broken into plates that move, collide, and subduct beneath each other, might be essential for long-term habitability. Plate tectonics regulates Earth's climate through the carbon cycle. When carbon dioxide accumulates in the atmosphere, chemical weathering of rocks gradually removes it, and subduction carries carbonate minerals deep into the mantle, where heat releases the carbon dioxide back through volcanic eruptions. This cycle acts as a thermostat, preventing runaway greenhouse or icehouse conditions. Without plate tectonics, a planet might lose this regulatory mechanism, making long-term habitability more difficult. But life is remarkably adaptable, and the conditions necessary for life might be far more flexible than our Earth-based experience suggests. On Earth, extremophiles, organisms that thrive in extreme environments, have shattered assumptions about where life can exist. Bacteria live in boiling hot springs at temperatures exceeding 200 degrees Fahrenheit. Microorganisms thrive in the frigid lakes beneath Antarctic ice. Life exists in hypersaline lakes many times saltier than the ocean, in acidic pools with pH levels that would dissolve metal, and in alkaline lakes caustic enough to burn skin. These extremophiles prove that life can adapt to conditions that would seem utterly hostile. Deep-sea hydrothermal vents host entire ecosystems based not on sunlight, but on chemical energy. Bacteria oxidize hydrogen sulfide and other chemicals spewing from the vents, and entire food chains build upon these chemosynthetic microbes. This discovery revolutionized thinking about where life could exist. A planet doesn't need sunlight reaching its surface to support life. Chemical energy from geological processes suffices. This realization expanded the search for life to include places like Jupiter's moon Europa and Saturn's moon Enceladus, which have subsurface oceans kept liquid by tidal heating. With no sunlight penetrating miles of surface ice, life might not even require a planet's surface. Europa and Enceladus demonstrate that subsurface oceans beneath ice shells can persist for billions of years. These hidden oceans might contain hydrothermal vents similar to those on Earth's ocean floor, providing chemical energy and raw materials for life. Enceladus actively vents water vapor, organic molecules, and salts into space through cracks in its ice, material that spacecraft have flown through and analyzed. The presence of organic molecules and evidence for hydrothermal activity suggests that Enceladus has at least some of the ingredients necessary for life. Titan, Saturn's largest moon, presents an entirely different possibility. Titan is the only moon in the solar system with a thick atmosphere, and it has lakes and rivers on its surface, but they're filled with liquid methane and ethane rather than water. The surface temperature, at about -300 degrees Fahrenheit, is far too cold for liquid water, but some scientists speculate that life might use liquid methane as a solvent instead of water, with biochemistry based on different chemical reactions more suited to cryogenic temperatures. Such life would be utterly alien, built on completely different principles than Earth's biology, but the basic requirements, a liquid solvent, chemical reactions, energy sources, might still allow life to emerge. The possibility of silicon-based life has long fascinated scientists and science fiction writers. Silicon sits directly below carbon in the periodic table and shares many chemical properties. Both form 4 chemical bonds, allowing them to create complex molecules. But silicon-based molecules are generally less stable and less diverse than carbon-based ones, particularly in the presence of water, which tends to break down silicon compounds. In environments without water, perhaps on a world with liquid hydrocarbons or even molten sulfur, silicon-based biochemistry might be possible, though it would function very differently from life on Earth. Life could potentially use different genetic molecules than DNA and RNA. These molecules store and transmit genetic information using a sugar phosphate backbone with nitrogen-based molecules attached. But chemists have synthesized alternatives called XNAS, xenonucleic acids, that use different sugars or even different backbone structures entirely. These artificial genetic molecules can store information and undergo evolution through selection, suggesting that life elsewhere might have invented entirely different solutions to the problem of heredity. Timescales matter enormously for life's emergence and evolution. On Earth, simple life appeared relatively quickly after conditions became favourable, perhaps within a few 100 million years of Earth's formation. This suggests that the transition from non-living chemistry to living organisms might not require unusual conditions or extraordinary luck. But the transition from simple microbes to complex multicellular organisms took vastly longer, roughly 3 billion years. The development of intelligence and technology required nearly all of Earth's history. A planet might easily develop microbial life, but remain stuck at that level indefinitely if conditions don't favour the evolution of complexity. Some planets might develop life, but lose it. Mars almost certainly had more favourable conditions for life billions of years ago when it was warmer and wetter. If life emerged during that time, it might have gone extinct when Mars lost most of its atmosphere and water, or it might persist in subsurface refuges where liquid water still exists in aquifers deep underground. Venus might have had habitable surface conditions early in its history before the runaway greenhouse effect transformed it into the hellscape it is today. Any life that emerged would have been sterilized, leaving no trace. Rogue planets, worlds ejected from their planetary systems to wander interstellar space, might still harbor life, despite receiving no light from any star. If a rogue planet is massive enough to retain a thick atmosphere, and if it has enough radioactive elements in its interior to provide heat, it could maintain liquid water beneath an ice shell indefinitely. Such planets would be invisible to most detection methods, dark worlds drifting through the galaxy, potentially harboring biospheres in their hidden oceans. Binary star systems, where two stars orbit each other, comprise about half of all stellar systems. Planets in these systems could orbit both stars at a large distance, experiencing light from two suns, or orbit one star closely while the other remains distant. Either configuration could potentially support habitable planets, though the complex gravitational dynamics make stable orbits more difficult to achieve and maintain over billions of years. The discovery of thousands of exoplanets has revealed that planetary systems come in astonishing variety. Hot Jupiters orbit closer to their stars than Mercury orbits our Sun. Super-Earths, a planet type absent from our solar system, appear to be common. Some systems pack multiple planets into orbits closer than Mercury's. This diversity suggests that habitable worlds might exist in configurations we haven't imagined, orbiting in stable zones within systems that look nothing like our own. Life could exist on other planets through countless permutations of chemistry, energy sources, solvents, temperatures, and planetary conditions. It might be carbon-based like us, or built from silicon or other elements. It might use water or methane or ammonia or substances we haven't considered. It might photosynthesize under a red sun or derive energy from chemical reactions in lightless seas beneath miles of ice. The universe is vast, ancient, and filled with planets and the basic ingredients for life: elements forged in stars, energy from stellar radiation or geological processes, and the simple passage of time exist everywhere. Whether life has taken advantage of these opportunities elsewhere remains the greatest unanswered question in science, but the conditions that could allow it exist on countless worlds scattered throughout the cosmos. How extraterrestrial plants could photosynthesize. Photosynthesis, the process by which plants, algae, and certain bacteria capture light energy and convert it into chemical energy, powers most of Earth's ecosystems. Green plants absorb sunlight, split water molecules, combine carbon dioxide from the air with hydrogen from the water, and produce sugars while releasing oxygen as a byproduct. This process transformed Earth's atmosphere from oxygen-poor to oxygen-rich over billions of years, enabling the evolution of complex animal life. Photosynthesis seems so central to life that we naturally wonder whether alien plants on distant worlds would photosynthesize in similar ways. The answer is nuanced. While capturing energy from starlight would likely be advantageous for life on any illuminated world, the specific chemistry and mechanisms of alien photosynthesis would differ dramatically depending on the star's properties, atmospheric composition, available pigments, and evolutionary history of each world. On Earth, photosynthesis centers on chlorophyll, a complex molecule containing magnesium at its center, surrounded by a ring structure that absorbs light strongly in the red and blue portions of the spectrum while reflecting green light, which is why plants appear green. Chlorophyll's absorption spectrum is not random but reflects the properties of sunlight. Our Sun is a yellow dwarf star with a surface temperature around 6,000 degrees Celsius, emitting light most strongly in the visible portion of the spectrum that our eyes evolved to see, with peak emission in the green-yellow range. Plants evolved pigments that absorb the abundant wavelengths while reflecting the less useful portions. But most stars in the galaxy are red dwarfs, cooler, smaller stars with surface temperatures around 3,000 degrees that emit most of their light in the red and infrared portions of the spectrum. A planet orbiting in the habitable zone of a red dwarf would receive much less visible light and far more infrared radiation than Earth receives from our Sun. Photosynthetic organisms on such a world would need to adapt to this shifted spectrum, likely evolving pigments that absorb infrared light rather than visible light. Capturing infrared photons presents challenges because each infrared photon carries less energy than a visible light photon. On Earth, chlorophyll uses two photons, absorbed at different stages of photosynthesis, to extract enough energy to split water molecules, which requires significant energy input. With lower energy infrared photons, alien photosynthesis might need to capture 3 or even 4 photons per reaction to gather sufficient energy, making the process less efficient. However, red dwarf stars are extremely common and extremely long-lived, shining for trillions of years compared to the Sun's 10 billion year lifespan. So even if photosynthesis is less efficient under red dwarf light, organisms would have enormous amounts of time to evolve and adapt. The pigments that absorb infrared light would likely appear black or very dark to human eyes because they would absorb nearly all visible light in addition to infrared. A forest on a red dwarf planet might be covered in black vegetation, maximizing absorption of every available photon from the dim red star. This is the opposite of Earth's green plants, which reject green light as insufficiently useful. On a planet where photons are precious, wasting any light would be disadvantageous, so evolution would favor organisms that capture everything. Conversely, planets orbiting hot, bright blue or white stars would receive intense ultraviolet radiation, along with visible and infrared light. Ultraviolet photons carry high energy, potentially too much energy, as UV light damages DNA and proteins. Photosynthetic organisms on such worlds might evolve pigments that specifically avoid ultraviolet absorption, reflecting or dissipating UV light while capturing only visible wavelengths. Or they might evolve protective mechanisms, UV-absorbing compounds in outer cell layers, extremely efficient DNA repair systems, or pigments that can safely handle high-energy photons by converting excess energy into heat or fluorescence. The color of alien plants would thus depend on their star's spectrum. Under orange K-type stars, plants might be red or orange, reflecting the most common light while absorbing other wavelengths. Under blue stars, plants might be yellow or orange. The specific colors would depend not just on what light is available, but also on what pigments evolution happens to discover and what combination of wavelengths provides optimal energy capture. Multiple pigments working together might be advantageous. On Earth, plants contain several pigments beyond chlorophyll, carotenoids, that absorb blue and green light, appearing yellow, orange, or red, and other accessory pigments that expand the range of useful wavelengths. These accessory pigments capture light that chlorophyll misses and transfer the energy to chlorophyll for use in photosynthesis. Alien plants might evolve even more diverse pigment systems, with perhaps 5 or 10 different pigments, each specialized for different wavelength ranges, collectively capturing a broader spectrum than Earth's photosynthetic organisms manage. The electron transport chains that actually convert light energy into chemical energy might use different chemistry than Earth's photosynthesis. On Earth, photosynthesis splits water molecules to extract electrons, releasing oxygen gas as waste. But water splitting is energetically demanding. It requires significant light energy input. An alien photosynthesis might use different electron donors that are easier to oxidize than water. Hydrogen sulfide, for instance, is easier to split than water and was likely used by early photosynthetic bacteria on Earth before oxygen-producing photosynthesis evolved. A planet with abundant hydrogen sulfide might develop photosynthetic life that remains at this stage indefinitely, producing elemental sulfur rather than oxygen as waste. Iron compounds, organic molecules, or even molecular hydrogen could serve as electron donors in alternative photosynthetic pathways. Each would produce different waste products. Iron photosynthesis might precipitate iron oxides. Organic-based photosynthesis might produce various carbon compounds, and hydrogen-based photosynthesis might produce protons that combine with other elements. None of these would generate an oxygen-rich atmosphere, demonstrating that photosynthesis doesn't necessarily equal oxygen production. The carbon source might also vary. Earth plants use carbon dioxide from the atmosphere as their carbon source, but CO2 concentrations vary dramatically across different worlds. Venus has a thick CO2 atmosphere, but is far too hot for life as we know it. Mars has thin atmosphere that's mostly CO2, but overall, CO2 availability is low due to the low pressure. A planet with very low atmospheric CO2 might require photosynthetic organisms that can concentrate and capture CO2 extremely efficiently, perhaps with specialized structures or enzymes far more effective than Earth's plants possess. Alternatively, alien photosynthesis might use carbon sources other than CO2. Carbon monoxide, methane, or even dissolved bicarbonate in water could provide carbon for building organic molecules. Each source would require different enzymatic machinery and would produce different end products. Methane-based photosynthesis might produce more complex hydrocarbons, essentially reversing the process that creates methane on Earth. ICO-based photosynthesis might build organic molecules through different chemical pathways than CO2-based photosynthesis uses. The physical structure of alien photosynthetic organisms might differ radically from Earth's plants. Trees evolved on land where structural support is needed to compete for sunlight, growing tall to shade competitors. But on a planet with perpetual dense cloud cover, blocking direct sunlight and providing only diffuse illumination, there would be no advantage to height. All locations would receive similar light levels. Plants might remain low-growing, perhaps forming dense mats rather than tall structures. On a planet with a very thin atmosphere, providing minimal structural support, perhaps Mars if it ever hosts photosynthetic life, organisms might need to be extremely sturdy and low-profile to withstand wind without atmospheric cushioning. Or on a high-gravity world, the structural challenges of growing tall might be prohibitive, keeping photosynthetic organisms close to the ground in spreading horizontal forms rather than vertical trees. Aquatic photosynthesis might dominate on ocean worlds. Earth's oceans contain vast amounts of photosynthetic organisms, phytoplankton, algae, and photosynthetic bacteria that drift or swim in the water column, capturing sunlight in the upper illuminated layers. On a world covered entirely by ocean, with no dry land, all photosynthesis would necessarily be aquatic. These organisms might evolve greater efficiency at capturing dim light filtered through water, or might develop gas-filled structures to regulate their depth, staying in the optimal light zone. Deep-sea photosynthesis might even be possible using not sunlight, but the faint light produced by hydrothermal vents or bioluminescence. On Earth, some photosynthetic bacteria near deep-sea vents use the faint thermal radiation from the hot vent fluids. This produces very little energy, but it demonstrates that photosynthesis isn't absolutely dependent on sunlight. An alien world with extensive hydrothermal activity might develop photosynthetic life that uses volcanic light, living in eternal darkness sustained by geothermal rather than solar energy. Bioluminescence-powered photosynthesis could create bizarre ecological cycles where organisms generate light through chemical reactions, other organisms use that light for photosynthesis, and the products of photosynthesis support the light-generating organisms. This would be less efficient than using a star's light directly. But on a rogue planet drifting through interstellar space with no star, such a system might be the only way photosynthesis could exist at all. The efficiency of photosynthesis varies greatly on Earth, with most plants converting only 1 to 2% of incoming light energy into chemical energy stored in sugars. This low efficiency reflects various constraints and trade-offs in the photosynthetic machinery. Alien photosynthesis might achieve higher efficiency through different molecular mechanisms, different pigment arrangements, or different metabolic pathways. Alternatively, on worlds where light is extremely dim, even 1 or 2% efficiency might be insufficient, driving evolution toward photosynthetic systems that capture and convert light more effectively. perhaps achieving 5 or 10% efficiency through molecular innovations not present on Earth. Timescales of photosynthesis might differ on other worlds. Earth's photosynthesis operates on timescales of milliseconds to seconds for individual reactions, constrained by the speed of enzyme reactions at Earth's temperatures. On a very cold world, reaction rates would be much slower. Photosynthesis might take minutes or hours for reactions that complete in seconds on Earth. This would mean slower growth rates and organisms that live life in slow motion from our perspective. On a hot world, reactions might proceed faster, allowing rapid photosynthesis and potentially faster growth, though this would also require dealing with the instability of biological molecules at high temperatures. The evolution of photosynthesis on Earth took hundreds of millions of years, with simpler forms appearing first and the complex, oxygen-producing photosynthesis we see in plants evolving later. On alien worlds, the evolutionary trajectory might differ. Perhaps photosynthesis evolves quickly, becoming established within the first billion years of life's appearance. Or perhaps it never evolves at all, with life remaining dependent on chemical energy from geological processes rather than light energy. Photosynthesis, while extremely useful, is not inevitable. It requires specific evolutionary innovations, including light-sensitive pigments, electron transport machinery, and carbon-fixing enzymes. A planet might have abundant life that never discovers photosynthesis, remaining microbial and chemosynthetic indefinitely. The seasonal variations on alien worlds would influence photosynthetic strategies. A planet with extreme axial tilt might experience dramatic seasonal variations in light availability, requiring photosynthetic organisms to either hibernate during dark seasons, store energy during bright seasons, or maintain alternative metabolic modes that don't require light. A tidally locked planet with one side permanently facing its star would have a permanent light side and permanent dark side, with photosynthesis possible only on the lit hemisphere or in the twilight zone between light and dark. The atmospheric chemistry would affect what wavelengths reach the surface. Earth's ozone layer absorbs harmful ultraviolet light, preventing it from reaching the surface. A planet without an ozone layer would expose surface organisms to intense UV, requiring either UV protective mechanisms or restriction of photosynthetic life to water, which naturally blocks UV. A planet with a different atmospheric composition, perhaps with sulfur compounds, nitrogen oxides, or exotic hazes, would filter light differently, creating different wavelengths available at the surface, and thus different optimal pigments for photosynthesis. How extraterrestrial plants could photosynthesize encompasses a vast range of possibilities shaped by stellar spectra, atmospheric filtering, available chemistry, and evolutionary contingency. From black plants absorbing every photon under dim red suns to colourful organisms reflecting abundant high-energy light under bright blue stars. From water-splitting oxygen producers to hydrogen sulfide users releasing sulfur. From rapid tropical growth to slow cold world metabolism, alien photosynthesis would adapt to each world's unique conditions while performing the same basic function, capturing light energy and converting it into chemical energy that powers ecosystems, potentially creating oxygen-rich atmospheres, modifying planetary chemistry in detectable ways, and revealing through their presence that life has discovered on distant worlds what it discovered on Earth. That starlight, properly harnessed through molecular machinery, shaped by billions of years of evolution, can power the chemical reactions that sustain living things, turning distant stars into energy sources for biology across the galaxy. How aliens could breathe different atmospheres. When we imagine aliens visiting Earth in science fiction, they often step out of their spacecraft and breathe our air without difficulty, or they wear helmets and breathing apparatus because our atmosphere is toxic to them. Both scenarios recognize a fundamental truth. the atmosphere that sustains one form of life might be useless or deadly to another. On Earth, oxygen is essential for most complex life, powering the high-energy metabolisms of animals through cellular respiration. But oxygen wasn't always abundant in Earth's atmosphere, and even today, many organisms live without it, thriving in environments where oxygen is scarce or absent. Understanding how aliens could breathe different atmospheres means understanding the relationship between atmospheric gases and metabolism, the chemistry of energy extraction, and the remarkable adaptability that evolution can produce when organisms face different atmospheric conditions. Earth's atmosphere is about 78% nitrogen and 21% oxygen, with trace amounts of argon, carbon dioxide, water vapor, and other gases. This composition seems normal because it's all we've known, but it's actually quite unusual from a cosmic perspective. Oxygen is highly reactive. It combines readily with many elements, forming oxides that are stable and chemically inert. Free oxygen shouldn't persist in a planet's atmosphere for long unless something continually replenishes it. On Earth, that something is photosynthetic life. Plants, algae, and photosynthetic bacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct. Without life constantly producing oxygen, Earth's atmosphere would gradually lose its oxygen as the gas reacted with rocks, metals, and organic molecules, eventually leaving an atmosphere dominated by nitrogen and carbon dioxide. For the first 2 billion years, or more of Earth's history, the atmosphere contained very little free oxygen. Early life evolved in this oxygen-poor world, using different metabolic pathways that didn't require oxygen. Even today, many organisms live in oxygen-free environments, deep in ocean sediments, in the intestines of animals, in waterlogged soils, where oxygen cannot penetrate. These anaerobic organisms use alternative molecules as the final electron acceptors in their metabolism. Some use sulfur compounds, reducing sulfate to hydrogen sulfide, the gas that smells like rotten eggs. Others use nitrates, producing nitrogen gas. Still others use carbon dioxide itself, producing methane. These metabolisms are less efficient than oxygen-based metabolism, releasing less energy per molecule of food consumed, but they work well enough to sustain life. An alien planet that never developed photosynthetic life might retain an oxygen-poor atmosphere indefinitely. Life on such a world would necessarily use anaerobic metabolism, breathing gases we would consider unusual or toxic. Hydrogen sulfide, lethal to most Earth animals, could serve as the oxidizing agent in alien metabolism. Organisms might inhale hydrogen sulfide and exhale elemental sulfur or some other sulfur compound. Their biochemistry would be built around sulfur chemistry, the way ours is built around oxygen chemistry. These aliens would find Earth's oxygen-rich atmosphere as toxic as we find hydrogen sulfide. Oxygen would react with their sulfur-based biochemistry, disrupting the carefully balanced chemical reactions that keep them alive. Methane represents another possibility. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms, and it exists as a gas at temperatures where water is liquid. Some Earth organisms produce methane as a waste product of their metabolism, and these methane-producing microbes, called methanogens, thrive in oxygen-free environments, like swamps, rice paddies, and the digestive systems of cattle. Methane is flammable in the presence of oxygen, but in an oxygen-free atmosphere, it's stable. A planet with abundant methane in its atmosphere might support life that uses methane in its metabolism, perhaps breaking down methane to extract energy or using methane as a raw material to build more complex organic molecules. Titan, Saturn's largest moon, has an atmosphere dense with nitrogen and methane, with no free oxygen. The surface temperature hovers around -180 degrees Celsius, cold enough that water is frozen as hard as rock, while methane exists as liquid in lakes and seas. If life exists on Titan, a big if, but not impossible, it would necessarily be adapted to breathe this nitrogen-methane atmosphere and might even metabolize in ways that involve liquid methane rather than liquid water. Such organisms would be completely incompatible with Earth's environment. Bringing them to Earth would be like throwing a fish into a furnace. The heat alone would destroy them before oxygen toxicity became an issue. Carbon dioxide-rich atmospheres present another scenario. Venus has an atmosphere that's about 96% carbon dioxide, creating a crushing surface pressure about 90 times Earth's atmospheric pressure, and a runaway greenhouse effect that raises surface temperatures to over 450 degrees Celsius. No life could exist in Venus's current conditions, but a cooler planet with a carbon dioxide atmosphere and might be habitable. Some Earth organisms already tolerate high carbon dioxide levels that would kill humans. Deep-sea hydrothermal vent communities, for instance, experience high carbon dioxide concentrations dissolved in water. Organisms adapted to such environments have specialized biochemistry that allows them to function despite the high carbon dioxide. Aliens from a carbon dioxide-rich world might metabolize in ways that involve carbon dioxide directly. Perhaps they would use carbon dioxide as an oxidizing agent, combining it with hydrogen-rich compounds to extract energy, producing methane or other hydrocarbons as waste products. Or they might use carbon dioxide as a raw material, building organic molecules from carbon dioxide the way plants do, but doing so as part of their metabolic processes rather than as a separate photosynthetic function. These aliens might find oxygen toxic and carbon dioxide essential, the opposite of most Earth animals. Ammonia is another gas that could potentially play a role in alien respiration. Ammonia is toxic to most Earth life, disrupting pH balance and interfering with normal biochemistry. But at lower temperatures, ammonia can exist as a liquid, and some scientists have speculated that ammonia could serve as a solvent for biochemistry on very cold worlds, potentially replacing water. An atmosphere with significant ammonia might support organisms that breathe ammonia, using it in their metabolism in ways we can barely imagine. The chemistry would be entirely different from oxygen-based metabolism, operating through different pathways and producing different waste products. Chlorine and fluorine, both highly reactive halogens, represent more exotic possibilities. These gases are extremely reactive and toxic to Earth life, but that's precisely because they're good at accepting electrons, the same property that makes oxygen useful for metabolism. An organism that evolved in an atmosphere containing chlorine or fluorine might use these gases the way we use oxygen, combining them with food molecules to extract energy. The waste products would be chlorides or fluorides rather than the water and carbon dioxide that Earth animals produce. Such organisms would find Earth's atmosphere lacking. Our oxygen, while reactive, wouldn't fit into their chlorine-based or fluorine-based biochemistry. They would suffocate in our air despite it containing a highly reactive gas. The partial pressure of gases matters as much as their chemical identity. Partial pressure is the pressure contributed by a specific gas in a mixture. For instance, Earth's atmosphere has a total pressure at sea level of about 1 atmosphere, and oxygen makes up 21% of that. So oxygen's partial pressure is about 0.21 atmospheres. Humans need oxygen at roughly this partial pressure to survive. Too little at high altitudes where atmospheric pressure drops and we suffer hypoxia, unable to get enough oxygen into our blood. Too much in pure oxygen at high pressure, and oxygen becomes toxic, causing seizures and lung damage. Aliens would have similar constraints based on their biochemistry. An alien that breathes hydrogen sulfide might need it at a specific partial pressure. Too little, and their metabolism cannot function efficiently. Too much, and it becomes toxic even to them. This means that even if two species breathe the same gas, they might not be able to share the same atmosphere if they require different partial pressures. An alien adapted to breathe oxygen at very low partial pressures, perhaps from a high-altitude environment or a planet with thin atmosphere, might suffocate in Earth's oxygen-rich air, not from lack of oxygen, but from oxygen toxicity. Temperature affects which molecules can exist as gases. On Earth, at our range of temperatures, nitrogen, oxygen, carbon dioxide, and water vapor exist as gases, while water also exists as liquid. On a much hotter planet, perhaps one close to its star, gases we don't encounter might be common. Sulfur compounds that are liquids or solids on Earth might be gases on a hot world. Metals like mercury or even iron could exist as vapor in the atmosphere of an extremely hot planet. Life on such a world, if it could exist at all, might breathe exotic gases that would condense into liquids or solids in Earth's relatively cool atmosphere. Conversely, on extremely cold worlds, gases that are common on Earth might be frozen solid. On Pluto, where temperatures drop to around -230 degrees Celsius, nitrogen, which makes up most of Earth's atmosphere, freezes into solid nitrogen ice. Pluto's thin atmosphere consists of nitrogen, methane, and carbon monoxide that sublimates from surface ices when Pluto is closest to the Sun in its elliptical orbit, then freeze back out when Pluto moves farther away. Life on such a cold world would need to breathe gases that remain gaseous at these extreme temperatures, or it would need to exist in warmer subsurface environments where different conditions prevail. The evolution of breathing mechanisms would differ based on atmospheric composition and pressure. On Earth, animals evolved lungs, gills, tracheal systems, and other specialized structures to extract oxygen from air or water. Fish gills expose blood to water flowing past thin membranes, allowing oxygen to diffuse from water into blood. Insect tracheal systems deliver air directly to cells through branching tubes. Mammalian lungs use millions of tiny air sacs to maximize surface area for gas exchange. Each system is optimized for extracting oxygen from Earth's atmosphere or water. Aliens breathing different atmospheres would evolve different respiratory structures optimized for their specific gases. An alien breathing a very dense atmosphere, perhaps with pressures many times Earth's, might have very small respiratory surfaces because gases would diffuse quickly at high pressure. An alien breathing a thin atmosphere might need enormous respiratory organs to capture enough of their necessary gas. An alien breathing a gas that dissolves poorly in their body, fluids might need respiratory pigments, molecules like hemoglobin in our blood, specifically designed to bind and transport their particular gas. Some aliens might not breathe at all in the sense of moving gases in and out of their bodies. Single-celled organisms on Earth absorb oxygen directly through their cell membranes without any respiratory system. An alien with a radically different body plan, perhaps resembling Earth's sponges or fungi more than animals, might absorb needed gases through its entire surface area, rather than through specialized breathing organs. Or an alien might rely entirely on anaerobic metabolism happening within its cells, never needing to extract gases from the environment at all, living on chemical energy stored in molecules absorbed from its surroundings. The possibility of breathing different atmospheres means that habitable zones around stars become more complex. The traditional habitable zone focuses on temperature, the range where liquid water can exist. But a habitability zone could be defined for any solvent and any metabolic gas. There's a methane habitability zone at different temperatures where methane is liquid. There's a hydrogen sulfide habitability zone where that gas exists at suitable pressures. There's an ammonia habitability zone at very cold temperatures. Each zone would support fundamentally different kinds of life adapted to its specific conditions. If humans ever encounter aliens, the atmospheric incompatibility would be one of the first obvious differences. We couldn't share environments without life support equipment. An alien from an ammonia world would need refrigeration and ammonia supplies to survive in Earth's environment. We would need oxygen supplies and temperature regulation to survive in theirs. Even communication would be affected. Sound travels differently in different atmospheric gases. In a dense carbon dioxide atmosphere, sound would be lower pitched and quieter. In a thin hydrogen atmosphere, sound would be higher pitched and travel faster. An alien's voice might be physically impossible for human ears to hear without electronic translation. How aliens could breathe different atmospheres ultimately reflects the diversity of chemistry and the flexibility of evolution. Life adapts to available conditions, and the chemistry that powers metabolism is not limited to oxygen and carbon dioxide. From hydrogen sulfide to methane, from ammonia to chlorine, from thin atmospheres to crushing pressures, from scorching heat to numbing cold, life, if it exists elsewhere, would develop respiratory systems suited to its world's specific conditions, breathing atmospheres that might kill us in seconds, while finding our oxygen-rich air as toxic and alien as we would find theirs, proving that the breath of life can take as many forms as there are worlds scattered across the universe. Why some planets have no moons. Of the 8 major planets in our solar system, 2 orbit the Sun without any natural satellites. Mercury and Venus have no moons. This seems puzzling at first. Mars, smaller than either Mercury or Venus, has 2 small moons. Earth has 1 large moon. The giant planets beyond Mars have dozens or even hundreds of moons. Why would some planets capture or retain moons while others remain moonless? The answer involves a complex interplay of gravitational dynamics, orbital mechanics, planetary formation history, and the specific environments in which these planets exist. The first factor to consider is proximity to the Sun. Mercury, the innermost planet, orbits at an average distance of only 58 million kilometers from the Sun. Venus orbits at 108 million kilometers. At these distances, the Sun's gravitational influence is overwhelming. For a moon to remain in a stable orbit around a planet, it must orbit within a region called the Hill sphere, the volume of space where the planet's gravity dominates over the Sun's gravity. The Hill sphere's size depends on the planet's mass and its distance from the Sun. The farther from the Sun, the larger the Hill sphere. The more massive the planet, the larger the Hill sphere. Mercury's Hill sphere extends only about 175,000 kilometers from the planet, less than half the distance from Earth to our Moon. Venus's Hill sphere is larger, extending about 1 million kilometers. But these regions are small compared to the Hill spheres of the outer planets. Earth's Hill sphere extends about 1.5 million kilometers. Jupiter's extends about 50 million kilometers. The small hill spheres around Mercury and Venus mean there's simply less space where a moon could maintain a stable orbit. But having a small hill sphere doesn't automatically prevent moon formation or capture. The real problem comes from tidal forces exerted by the Sun. Tidal forces arise because gravity weakens with distance, creating a differential pull across an extended object. The Sun's tidal forces on a potential moon of Mercury or Venus would be much stronger than the tidal forces experienced by moons of more distant planets, simply because these inner planets are so close to the Sun. These solar tides compete with the planet's own gravity for control of the moon's orbit. Over time, solar tidal perturbations can destabilize a moon's orbit, causing the orbit to become increasingly elliptical or inclined. Eventually, the moon might either crash into the planet, drift away into an independent orbit around the Sun, or get ejected from the system entirely. The closer the planet is to the Sun, the stronger these destabilizing effects become. There's a critical region around each planet, well inside the Hill sphere, where orbits can remain stable over billions of years despite solar perturbations. This region is typically only about 1/3 to 1/2 the radius of the Hill sphere. For Mercury, this stable region extends perhaps only 60,000 to 80,000 kilometers from the planet. For Venus, perhaps 300,000 to 500,000 kilometers. Any moon orbiting farther out would likely be stripped away by solar tides over geological time. But this raises another question. Why didn't small moons form or get captured in these inner stable regions? To understand this, we need to consider how moons form in the first place. There are three primary mechanisms: co-formation, where the moon forms from the same disk of material as the planet; capture, where the planet's gravity snares a passing object; and giant impact, where debris from a massive collision coalesces into a moon. The giant impact hypothesis explains Earth's moon. About 4.5 billion years ago, a Mars-sized object called Theia collided with the young Earth. The impact ejected enormous amounts of material into orbit around Earth, and this debris quickly coalesced into the moon. This mechanism requires specific conditions, a large impactor at the right velocity and angle. Mercury and Venus likely experienced giant impacts during the chaotic early solar system, but any moons formed from such impacts would face additional challenges. Mercury's proximity to the Sun means that debris from an impact would orbit in an environment where solar tides are extremely strong. Material orbiting Mercury would experience differential forces from the Sun that could prevent it from coalescing into a moon, or could destabilize any moon that did form. Additionally, Mercury's slow rotation, it rotates once every 59 Earth days, means it couldn't have transferred much angular momentum to a moon through tidal interactions, which helps stabilize moon orbits over time. Venus presents a different puzzle. It's larger than Mercury, more massive, and farther from the Sun, with a correspondingly larger hill sphere and stable region. Venus should be able to retain a moon more easily than Mercury, yet Venus is moonless. Several theories attempt to explain this anomaly, and the answer might involve Venus's unique rotation. Venus rotates incredibly slowly. One Venusian day lasts 243 Earth days, and it rotates backward relative to its orbital motion, a condition called retrograde rotation. This retrograde rotation is unusual and likely resulted from one or more giant impacts that altered Venus's spin. If Venus once had a moon formed from such an impact, the combination of Venus's slow retrograde rotation and solar tides could have caused the moon to spiral inward rather than outward. On Earth, tidal interactions with the moon cause the moon to gradually recede. It's moving away from Earth at about 3.8 centimeters per year. This happens because Earth's rotation is faster than the moon's orbital period, so tidal bulges on Earth are carried ahead of the Earth-Moon line, pulling the moon forward in its orbit and transferring angular momentum. For a moon orbiting retrograde Venus, or orbiting a very slowly rotating Venus, the tidal dynamics work differently. The tidal bulges would lag behind rather than lead, causing the moon to lose orbital energy and spiral inward toward the planet. Eventually, the moon would cross the Roche limit, the distance inside which tidal forces overcome the moon's self-gravity, and be torn apart. The fragments would either fall onto Venus or spread into a ring system that gradually decayed, with particles spiraling down to the planet's surface over millions of years. If Venus had a moon in the distant past, this mechanism could have destroyed it billions of years ago. Alex Alemi and David Stevenson proposed this scenario in 2006, suggesting that Venus's slow retrograde rotation would cause any moon to spiral inward and be destroyed within tens of millions of years. Their calculations showed that even a large moon, similar in size to Earth's moon, would meet this fate if Venus rotated slowly enough. The giant impact that created the moon might also have been responsible for slowing or reversing Venus's rotation, setting up the conditions for the moon's eventual destruction. Capture represents another moon formation mechanism, but it faces significant challenges. For a planet to capture a passing asteroid or other object, something must remove energy from the object's orbit during the close encounter, Otherwise, the object simply swings past the planet and continues on its way. Energy can be removed through atmospheric drag if the planet has a thick atmosphere, through gravitational interactions with existing moons in a three-body interaction, or through tidal forces if the encounter is extremely close. Mercury has essentially no atmosphere, so atmospheric capture is impossible. Venus has a thick atmosphere, but capturing an object large enough to be considered a moon rather than just a small asteroid would require the object to pass through the upper atmosphere at just the right velocity and angle, an unlikely scenario. Mars's two small moons, Phobos and Deimos, might be captured asteroids, but they're tiny. Phobos is only about 22 kilometers across and Deimos about 12 kilometers. Mars likely captured them during the early solar system when more debris was available and orbital dynamics were more chaotic. For Mercury and Venus, the combination of their locations in the inner solar system, where fewer large objects were available for capture, and the difficulty of the capture process itself, meant that gravitational capture of moons was unlikely. The inner solar system was largely cleared of debris early in solar system history, as objects either accreted into planets, fell into the Sun, or were ejected to the outer system through gravitational interactions with the growing planets. The composition and formation history of the inner planets also matters. Mercury, Venus, Earth, and Mars formed from the inner portion of the protoplanetary disk, where temperatures were too high for ice to condense. These planets formed primarily from rocky and metallic materials. The giant planets formed farther out, where ices could exist, providing more material for planet and moon formation. The abundance of material in the outer solar system, both for forming the planets themselves and for forming moons, was simply greater than in the inner solar system. The giant planets likely formed their large regular moons, the major satellites that orbit in the planet's equatorial plane, from circumplanetary disks, miniature versions of the protoplanetary disk that surrounded the young Sun. These disks contained enough material to form multiple large moons. Jupiter's four Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610, formed this way. Saturn's major moons, including Titan, formed similarly. The inner planets, with less mass and forming in a region with less available material, likely didn't have substantial circumplanetary disks, making it difficult to form moons through this mechanism. Exoplanet studies have revealed that moonless planets might be quite common. Many exoplanets discovered so far are hot Jupiters, gas giants orbiting extremely close to their host stars, often closer than Mercury orbits the Sun. These planets, despite being massive, likely have no moons because the extreme proximity to their stars creates even more severe tidal effects than Mercury experiences. Any moons would be quickly stripped away by stellar tides. Some hot Jupiters may have had moons when they formed farther from their stars, but lost them as the planets migrated inward to their current close-in orbits. Other exoplanets orbit in the habitable zones of their stars at distances where moons could potentially remain stable. Whether these planets have moons depends on their formation history, the availability of material for moon formation, and the dynamical environment in which they formed. Detecting exomoons, moons orbiting exoplanets, remains at the edge of current observational capabilities, though several candidates have been proposed. As detection techniques improve, we'll learn whether most planets have moons or whether moonless planets are actually the norm. The absence of moons around Mercury and Venus is not a deficiency, but rather a natural consequence of where these planets are located and how they formed. Their proximity to the Sun creates an environment where moons cannot easily form or survive over billions of years. Any moons that might have existed in the early solar system were likely destroyed by solar tides, spiraled into the planets due to tidal interactions with slowly rotating worlds, or were ejected from unstable orbits. The planets that do have moons, Earth, Mars, and especially the giant planets, possess them because they orbit farther from the Sun, where Hill spheres are larger, solar tides are weaker, and the environment is more conducive to moon formation and retention, showing that the presence or absence of moons depends not on the planet's inherent qualities, but on the orbital and environmental context in which the planet exists, making our own moon's existence not a given, but rather the result of a fortunate combination of location, timing, and the specific collision that created it billions of years ago. Why one side of the moon always faces Earth. If you look at the moon on any clear night, you'll see the same familiar pattern of light and dark regions, the features we call the man in the moon or the rabbit, depending on cultural interpretation. This pattern never changes. The same side of the moon perpetually faces Earth. There is no natural rotation of the moon that would show us different faces throughout the month. Ancient astronomers noticed this peculiarity thousands of years ago, and for centuries it seemed like a remarkable coincidence. Why would the moon's rotation period exactly match its orbital period around Earth, both taking about 27 days? The answer involves no coincidence at all, but rather a physical process called tidal locking that inevitably synchronizes the rotation and orbit of any moon close enough to its planet. Tidal locking occurs because of tidal forces, the same forces that create ocean tides on Earth. Tidal forces arise because gravity weakens with distance. The side of Earth facing the moon experiences slightly stronger gravitational pull from the moon than Earth's center does, and Earth's center experiences slightly stronger pull than the side facing away from the moon. This difference in gravitational strength across Earth's diameter creates the tidal force that stretches Earth slightly, raising bulges on both the near and far sides. The same process works in reverse. Earth's gravity creates tidal bulges on the moon, though without oceans these bulges are in the solid rock itself. The moon is slightly elongated, stretched along the Earth-Moon line, with the long axis about 20 meters longer than the short axis. If the moon rotates relative to Earth, these bulges try to rotate with the moon, but Earth's gravity pulls on the bulges, trying to keep them aligned with Earth. Imagine the moon rotating slightly faster than once per orbit. As it rotates, the tidal bulge tries to rotate ahead of the Earth-Moon line, but Earth's gravity pulls more strongly on the closer bulge, creating a torque that opposes the rotation, slowing the moon down. This gravitational torque acts like friction, steadily dissipating the moon's rotational energy. The energy doesn't disappear. It converts into heat through internal friction as the moon flexes slightly, warming the lunar interior by tiny amounts. Over millions of years, this process slows the moon's rotation until it matches the orbital period. Once synchronized, the same side always faces Earth. The tidal bulges align perfectly with the Earth-Moon line, and there's no more torque trying to change the rotation. This is the state the moon reached long ago. The moon is tidally locked to Earth, rotating once on its axis in exactly the same time it takes to orbit Earth once, both periods equal to about 27.3 days. From the moon's perspective, Earth hangs nearly motionless in the lunar sky, drifting slightly back and forth due to libration, small oscillations caused by the moon's slightly elliptical orbit and tilted axis, but never rising or setting. If you stood on the near side of the moon, Earth would always be visible. If you stood on the far side, Earth would never be visible, hence why that hemisphere is sometimes mistakenly called the dark side, though it receives just as much sunlight as the near side. The timescale for tidal locking depends on several factors. Larger tidal forces lock a moon more quickly, closer moons experience stronger tidal forces and lock faster than distant moons. Moons with more internal friction, perhaps from molten interiors, dissipate energy more efficiently and lock faster. For the moon, calculations suggest that tidal locking occurred relatively early in the Moon's history, within the first 100 million years or less after its formation. By the time complex life evolved on Earth, the Moon had already been showing the same face toward our planet for billions of years. Tidal locking doesn't just affect the Moon, it's common throughout the solar system. Most major moons are tidally locked to their planets. Jupiter's 4 large Galilean moons, Io, Europa, Ganymede, and Callisto, all show the same faces to Jupiter. Saturn's large moon Titan is locked. Neptune's moon Triton is locked. In fact, of all the major moons in the solar system, almost everyone is tidally locked to its planet because they've had billions of years for tidal forces to synchronize their rotations. Some moons have been locked into more complex rotations through resonances with other moons. Mercury, though not a moon, is locked in a 3-to-2 resonance with the Sun. It rotates 3 times for every 2 orbits, a more complex tidal lock. Pluto and its large moon Charon are mutually tidally locked. Each shows the same face to the other always. Pluto rotates once per orbit, and Charon orbits once per Pluto's rotation, so they're perpetually facing each other across their orbit. The tidal locking process also affects Earth, though much more slowly because Earth is more massive than the Moon. The Moon raises tidal bulges on Earth, primarily in Earth's oceans, creating the familiar ocean tides. Earth rotates faster than the Moon orbits. A day is 24 hours, while the Moon's orbital period is about 27 days. This means Earth's rotation carries the tidal bulges ahead of the Moon's position. The bulge closer to the Moon is slightly ahead of the direct Earth-Moon line, and the Moon's gravity pulls backward on this bulge, creating a torque that slows Earth's rotation. This effect is measurable. Earth's rotation is slowing by about 2 milliseconds per century. Days are getting gradually longer as Earth loses rotational angular momentum. The angular momentum doesn't vanish, it's transferred to the Moon's orbit. As Earth slows down, the Moon speeds up slightly in its orbit, and a faster orbital speed means the Moon moves to a higher orbit. The Moon is currently receding from Earth at about 3.8 centimeters per year, precisely measured by bouncing laser beams off retroreflectors left on the lunar surface by Apollo astronauts. This process has been operating throughout Earth's history. Early in Earth's history, when the Moon was much closer, days were much shorter, perhaps only 5 or 6 hours long, and the month was shorter too. Ancient corals and other organisms that leave daily growth rings provide evidence for shorter days in the distant past. Going forward, the process will continue. In the far future, if given enough time, tens of billions of years, Earth's rotation would eventually slow to match the Moon's orbital period. At that point, Earth would be tidally locked to the Moon, just as the Moon is now locked to Earth, with the same face of Earth always facing the Moon. However, this will never happen because the Sun will evolve into a red giant in about 5 billion years, long before Earth could become tidally locked to the Moon. The expanding Sun will engulf the inner solar system, making the question of Earth's rotation academic at best. The tidal locking of the Moon has significant consequences for lunar exploration and observation. The far side of the Moon remained completely unknown until spacecraft flew around it. The Soviet Luna 3 probe in 1959 captured the first images of the far side, revealing a surface surprisingly different from the near side. The far side has many more craters and far fewer of the dark volcanic plains called Maria that dominate the near side's appearance. This asymmetry likely relates to the Moon's tidal locking. The near side experienced more volcanic activity, possibly because Earth's gravity affected the Moon's internal structure and thermal evolution. Communication with spacecraft on the lunar far side requires relay satellites because direct signals cannot reach Earth from there. China's Chang'e 4 mission, which landed on the far side in 2019, used a relay satellite positioned beyond the Moon to maintain communication. Future lunar bases on the far side would face this same communication challenge, requiring either relay satellites or cables running over the lunar surface to the near side. Tidal locking affects more than just moons. Many exoplanets discovered orbiting close to their stars are likely tidally locked, with one hemisphere permanently facing the star in daylight, while the other remains in eternal darkness. These planets, particularly those orbiting red dwarf stars, where the habitable zone is very close to the star, would have extreme temperature contrasts between their day and night sides. Understanding how atmospheres redistribute heat on tidally locked planets is crucial for assessing their potential habitability. The fact that one side of the Moon always faces Earth is not a lucky accident, but the inevitable result of physical forces operating over immense timescales. Every moon close enough to its planet will eventually lock, synchronizing its rotation to its orbit. The Moon reached this state billions of years ago, and it will remain locked for the remaining lifetime of the Earth-Moon system. The same face that witnessed Earth's formation, the rise of life, the age of dinosaurs, and the emergence of humanity will continue watching Earth for billions of years to come, held in place not by chance but by the patient, inexorable work of tidal forces that have shaped orbital dynamics since the solar system formed, creating the familiar face we see in the night sky every month, unchanging and eternal from our human perspective, yet itself the product of changes stretching across geological deep time.